Hi everyone, thanks for watching this video. I'm going to tell you about some of Square's law bounds on ultra-sparse random graphs. This is joint work with my advisor, Professor Katari at Princeton and Aaron Pedestrian at U Chicago. And let's get started by revisiting click the seminal question in average case complexity. In this work, we consider random graph GMP, where it's just the graph distribution in which we sample each edge with a probability P, IID. And if we sample graph from GN 1/2, each edge appears with probability 1/2, and add a click of size K. The planar click question asks when can we find the planar click? And this has been studied since the 80s. And here's what we know. Information theoretically, we know that with higher probability, a random graph from GN 1/2 has largest click of size 2 log n. And this we call the information threshold. Algorithmically, we know that the click can be found as long as k is at least some constant times root n, and we call this the algorithm threshold. However, this leaves an in-between regime between 2 log n and 0 n, and it's natural to wonder what happens in this middle regime. And here's an example of the information versus computation gap. And this turns out to be a phenomenon quite universal, not just for planar click. For example, it also happens for refutation of random CSP. If we consider a random 3SO instance, we know that its with high probability is unsatisfiable once we have linear number of clauses. However, the best non-efficient algorithm requires the number of clauses to be at least n to the 1.5. And there are a lot more examples, including community detection and colorings and PCA type of problems. In this work, we are going to focus on independent set on G and D over N, or you can also think of it as planar click question on very dense graph, where each edge appears with probability 1 minus D over N if you consider the complement of our question. And here's what we know. For G sample from G and D over N, the largest independent set is of size n log D over D. And the algorithmic question we consider here is what's the best upper bound we can certify? Here, when we say certifying an upper bound on the independent set, we are looking for an algorithm that takes in a graph and outputs a number such that this number is always an upper bound on the size of the independent set of the graph. And for this question, we actually know that there is a special algorithm that works to show independent set to be of size at most 2n over root d. And here's roughly how it works. We start by considering the center adjacency matrix, which is for each edge that appears in the graph sample, we put 1 minus d over n, and minus d over n otherwise if the edge is missing. And the crucial claim is that the independent set of the graph has size at most n over d times the spectral norm of this matrix. And using results from random matrix theory, we know that this matrix has norm at most 2 root d with high probability. So this gives us an upper bound of size 2n over root d for G sample from G and D over n. Now that we know this 2n over root d bound, a natural next step is to ask whether we can significantly improve from here. And to answer this question, we are going to take a detour and introduce sum of squares STP a little bit. This is a family of increasingly powerful semi-definite programming. And it's usually parameterized by sum of square degree. We know that degree d sum of squares runs in time n to the order d. And the sum of squares degree gives us a natural interpolation from polynomial time commutation to exponential time, as constant degree sum of squares runs in polynomial time. And if we take the degree of SOS to be n, this runs in exponential time now. And we know that starting from degree 2 SOS, sum of squares already captures linear programming and special methods. And why do we want to mention this? It turns out that this is quite powerful a family of algorithms that captures many best known and even optimal algorithms in both the worst case and average case setting. So this is a reasonable candidate, it appears, to study, to hope for extensions if you one wish to improve from this 2n over root d bound that we saw earlier for independent set. Or maybe more generally, one can even study lower bounds against sum of squares to provide hardness result. Consider how powerful it is as a family of algorithms. And this is indeed what we consider in this work. We tweak the question a little bit and ask for whether higher degree sum of squares can improve from this 2n over root d bound. And here's what we know previously on sum of squares and its performance for these average case problems. For distinct graph problems, which is random graph with average degree theta n, sum of squares has been, or even higher degree sum of squares has been relatively well understood here, starting from the planar clique and refutation of random CSP and several other questions. However, all these previous techniques already fail if we look at random graph that is slightly sparser, like even of average degree n to the 1 minus epsilon. And in this regime, there are two previous works that consider this, and one word that's closely related to us is the one that studies independent set for sparse random graph for when the average degree is at least polylog. However, besides those works, like if we look at super sparse random graph, G and D over N, when D is a constant, large but bounded constant, our understanding is relatively limited, and the best we know here is most of what we know here is limited to degree 2 sum of squares or basic STP. And here we know several results for commutation and its related problems. Degree 4 sum of squares is mostly unknown, even if we just slightly upgrade from degree 2, but there is some previous result on mass cut. However, we want to emphasize that all these previous analysis do not generalize to higher degree sum of squares. And the best we know before is on degree 4 even. And this is really the focus of our work. We show that in this ultra sparse regime of G and D over N for some large constant D, degree D sum of squares fails to solve the independent set question. In particular, it's going to give an independent set of value n over root d times DSOS square. So let me unpack this statement in a bit. So our result is most meaningful when DSOS is at most some constant times d to the 1/4, because this is where we give an SOS value bigger than the information threshold of 2n log d over d to show that there is a separation in the SOS value and the true value. So there is a SOS gap here. And our work, along with the previous works for Penny-Click and independent set in polylog degree, gives a picture of sum of squares performance for independent set question. And focusing on our work, we also give the picture of sum of squares harness for independent set when D is constant. We really show that sum of squares of degree less than D to the 1/4 fails to solve this mass independent set question for random graph from G and D over N. And here is a general sketch of the curve for the SOS value, a 10-bar walk. And now I'm going to sketch a bit the main technical ingredient in our work that works to prove this result. To get started, we are going to consider how we study higher degree sum of squares. As we saw in the algorithm part just now, the algorithm crucially relies upon the special norm bound of the for random matrices. For example, just the adjacency matrix that we consider there, or the center adjacency matrix. And this is closely connected to algorithms. It turns out that this connection is still valid if we ask for average case hardness. And here's one high-level intuition. The lower boundary we strive to prove, they should ideally not break the known algorithms. So it should capture special reasoning and therefore connected to the ingredient there, which is special norm bounds for random matrices. And here's a high-level view for some average case sum of squares bounds. We know that by definition, sum of squares captures special algorithms. But on the other hand, for higher degree sum of squares, we can also just view it as a gigantic matrix of dimension n to the order d by n to the order d. And each entry of this known matrix, we can think of it as a polynomial of degree d log n of the underlying input. One example is for a given set S, the independent set indicator can be written as a polynomial of the graph input. And here's the polynomial. So notice that this indicator is 1 only if S is an independent set in the graph, and 0 otherwise. That said, higher degree sum of squares lower bounds also usually just boil down to a systematic understanding of all such matrices. And we are going to elaborate on this in a bit. And this is our main technical work. And okay, now let me instantiate what we mean by these matrices. We are going to consider graph matrix, which is a collection of random matrix with polynomial entries. And here's a general setup. We are going to assume that there is an underlying input G, for example, random graph. And graph matrix is a matrix such that each entry is a polynomial of inputs in G. And one baby example is just the adjacency matrix. This is just the linear function of the graph. And of course, we are going to look at some more complicated generalizations of this. And here's a formal definition. Graph matrix is usually associated with a diagram that we call a shape. And in this shape, there are two sets of special label vertices that correspond to row and column indices of the matrix. And the matrix is going to be indexed by order tuples in N. So S is an order tuple in N and also T. And now for each entry, we are going to write a polynomial from the associated diagram. And yeah, this is going to be clear in the next slide. But one important remark that we want to make here is that one motivation of looking at such matrices is that they form a basis for matrix value functions, including the sum of squares moment matrix that we are interested here. And here's this one baby example, which is the Z-shaped matrix that we are going to consider here. We are going to consider the following instantiation, where the left-hand side, the vertices in S, receive labels A and B, and the vertices on the right label set receive labels C and D. And we are going to sum over all possible labels of the middle vertex T. And for each label T, we are going to put the entry of GAC times GCT times GBT times GBT, where each of them is the associated Fourier character of the underlying linear graph. And we want to observe here that in general, these matrix entries are highly non-independent. And for example, one way to see this is that this is a matrix of dimension n squared by n squared, but we only really have n squared base of randomness from the random graph samples. And this non-independence or the correlation across entries really prevents us from applying most results in random matrix theory. And just to recap, like this diagram, also this diagram language also captures the adjacency matrix. For example, it is just simple line graph with two vertices. It's a toy example. And it turns out that we are not the first group of people studying these matrices. They have been intensively studied in the previous investigation for sum of squares, starting from the Penny Creek in 2015, 2016. However, all these previous non-bounds, they're really just known for the dense regime, the dense graph when from GN1 half, for example, and they are lossy in various factors. That said, we do know several tight non-bounds, but they are really just known for specific example of graph matrices or polynomials. For example, we have really tight non-bounds for adjacency matrix always analog, like non-backtracking operator. But these are only known for specific examples, and they are far from being sufficient for understanding high degree sum of squares. And here's really just the main ingredient of our work. We showed improved non-bounds for graph matrices in the ultra sparse regime when the underlying input comes from G and D over N for D being constant. And we show that in this regime, the non-bound continues to be tightly determined by the vertex separator, which is also the non-bound governing quantity in the dense regime. So on a high level, a set of vertices is a vertex separator. If for a graph with two labeled set of vertices S and T, any path from S to T pass through some vertex in this set of vertices. And here we're going to do a tiny comparison with previous non-bounds. As we said, previous non-bounds are lossy in various ways. However, the non-bounds that we give here are tied up to absolute constant per vertex or edge of the underlying polynomial. And an example is that for adjacency matrix, there is a 2 root D bound that is tight, and in this machinery, we give a bound of 4 root D. But it can actually be tightened to be 2 root D if needed, even within our machinery. And as we said previously, like previous tight non-bounds are only known for specific examples, and our non-bound here actually applies generally to matrices with polynomial entries of the underlying random graph set. And they apply when in the super sparse regime when G and D, when your graph comes from G and D over N for D being large but bounded constant. And here is a informal statement of what we prove about these matrices. For convenience, we are going to scale up each Fourier character such that each edge gives character root n over d if the edge is present, and minus root d over n otherwise. This is just a convenient scaling for us, and we show that in this scaling, with probability at least 1 minus 1 over poly n, the norm of the graph matrix is at most some constant to the number of vertices, absolute constant, independent of D and independent of D, uh, and the graph actually, independent of D and the shape, such that the norm is given by maximizing over all possible vertex separator, root n to the number of vertices outside the separator, and root n over D to the number of edges inside the separator. And here we are going to show how we can apply this result for the Z-shaped matrix that we saw just now. If we pick these two pink vertices to be the vertex separator, they do not correspond to any non-bound in this statement because they're not a vertex separator. There is the top pass from left to right, there's unblock. However, if we put these two other pink vertices, these correspond to a vertex separator now, and this gives us non-bound root n cube because there are three vertices outside the separator and there is no edge contained within the separator. However, they are not the true non-bound quantity, as one may consider these other three vertices separator that gives non-bound root n squared times root n over d squared. And it turns out that this is indeed the right non-bound for this Z-shaped matrix. And now let me look at a bit of the talk. In the beginning of the talk, we mentioned like information versus computation gap is quite a universal phenomenon, and it happens for pentacritic, and it depends for sparse random graph and many other questions. And one way to provide evidence for this information versus computation gap is to show rigorous sum of square thresholds. And towards doing so, one requires a systematic and sharp understanding of these correlated random matrices called graph matrices. And this is the main progress of our work. Yeah, I want to thank you for watching this video, and feel free to reach out to us if you have any question about this work. Thank you.